When you picture astronauts hanging out aboard the International Space Station, what comes to mind? Probably a serene, totally silent float through an empty void, right? Well, welcome to today's Explainer, where we're going to completely flip that idea on its head. The reality is actually a violently high-speed, incredibly high-stakes physics experiment. The mechanics keeping this 450-ton orbital laboratory alive are frankly exhilarating. So let's dive right in and break down the incredible forces at play.
We absolutely have to start by shattering a very common misconception. It's super easy to look at footage of astronauts floating around the ISS and just assume, oh, there's zero gravity up there in the vacuum of space. But that literally couldn't be further from the truth. Gravity is very much active exactly where the ISS orbits. So you're probably wondering, why on Earth aren't the astronauts pinned to the floor? The answer starts with a pretty surprising number, 90%. Get this. At 400 kilometers, or about 250 miles above the Earth's surface, our planet's gravitational pull is still roughly 90% as strong as it is right here, where you and I are sitting. The ISS and everything inside it is constantly, relentlessly being pulled downward by the Earth. Gravity hasn't vanished at all. So here is the crucial takeaway. They aren't floating. They are actually in a state of continuous free fall, which is what we call microgravity. The station is literally falling toward Earth, but, and this is the key, it's moving sideways at such a ridiculous speed that the downward curve of its fall perfectly matches the curve of the planet itself. It's essentially falling endlessly around the Earth rather than straight down into it. Think about it like a roller coaster. You know that intense stomach-in-your-throat sensation you get right when a coaster crests a steep hill and rapidly drops? For that split second, as you accelerate downward with the car, you feel weightless because the seat literally drops away from you. Well, the astronauts are experiencing that exact same effect, except they feel it permanently because they are falling right alongside the station with absolutely nothing pushing back against them. Now, to pull off this endless fall without actually plummeting into the ground, you need immense horizontal velocity. The space station is cruising at a staggering 28,000 kilometers per hour. That's about 17,500 miles per hour. To put that into perspective, they are traveling roughly 7.6 kilometers every single second. It is absolutely mind-blowing. And you know what's crazy? This brilliant physics concept actually dates all the way back to the 17th century with Sir Isaac Newton. Newton theorized that if you fired a cannonball horizontally off a high enough mountain, gravity would naturally pull it down. But if you fired it fast enough, the planet's surface would curve away beneath it at the exact same rate the ball was falling. The ISS is basically Newton's cannonball. It perfectly balances that inward centripetal force directed toward Earth's center with its massive orbital velocity. Which brings us to Section 1, the invisible antagonist, atmospheric drag. So perfect orbital velocity sounds great on paper, but it isn't quite enough. Why? Because the space station isn't actually hanging out in a perfectly empty void. It sits in a layer of the atmosphere called the thermosphere. And even though molecules up there are incredibly scarce, there are just enough oxygen molecules constantly colliding with the station to act like a giant invisible brake. This friction decelerates the massive station by about 5 centimeters per second, which might not sound like a lot, but it causes the ISS to lose roughly 100 meters, or 328 feet, in altitude every single day. Gravity is, very slowly, winning the fight. And making this whole situation even more chaotic is the sun. Atmospheric density isn't a static thing. It's closely tied to the 11-year solar cycle. During periods of high solar activity, the atmosphere heats up and swells like a balloon, pushing denser air higher up and increasing the drag on the ISS by a full order of magnitude. Throw in things like the midnight mass density maximum, which increases atmospheric density at the equator just after midnight, and various semi-annual variations, and satellite orbits can get shifted by up to 800 meters. It's an incredibly dynamic and unpredictable obstacle course. Let's look at Section 2, the mechanics of survival, attitude versus altitude. To fight off this constant orbital decay, we need some serious mechanical intervention. Engineers essentially have to manage two completely different aspects of the station's motion, attitude and altitude. Attitude control is all about orientation, managing the station's angle, roll, pitch, and yaw, keeping the whole thing perfectly balanced without actually changing its height. Altitude control, on the other hand, is the sheer brute force required to actively shove the station back up into its proper orbit whenever atmospheric drag inevitably pulls it down. Take a look at these sleek, rapidly spinning disks. These are the control moment gyroscopes, or CMGs. Instead of constantly firing off thrusters to keep the station balanced, which honestly would waste a ton of precious fuel, the ISS uses these massive gyroscopes to manage its momentum. They silently, efficiently absorb external torques and keep the station totally stable as it speeds through space. The ultimate goal of those spinning gyroscopes is to maintain what's called the torque equilibrium attitude, or TEA. You can think of it as the ultimate sweet spot. It's the perfect balance point where the aerodynamic drag and the force of gravity essentially cancel out external torques. The ISS actually allows itself a very slight attitude error, sometimes pitching down a bit depending on what cargo or crew vehicles happen to be docked, just to keep that momentum vector completely stable across an entire orbit. Finally, Section 3, the SpaceX Dragon Reboost. Okay, so while gyroscopes gracefully handle the balance, they can't solve the altitude problem. To fight that daily 100-meter drop, the ISS has historically relied on the Russian Zvezda module's thrusters or visiting Progress and Cygnus spacecraft to literally push the station higher. But recently, a totally new method entered the chat. A SpaceX Dragon capsule docked carrying a brand new boost kit tucked right inside its trunk, introduced in fall 2025. It uses rear-facing Draco engines perfectly aligned with the station's velocity vector. And, the coolest part, they run on hypergolic propellant, hydrazine and nitrogen tetroxide, which literally explodes on contact, providing the massive brute force needed to shove a 450-ton station back upwards. Look at the data from this test back in November 2024. Over a 12-minute burn, the SpaceX Dragon successfully nudged the massive space station higher. It actually increased its apogee, that's its furthest point from Earth, by 0.07 miles, and its perigee, the closest point, by 0.7 miles. It's a highly precise, incredibly violent intervention that pushes back against the thermosphere's drag in a truly spectacular way. But as amazing as all this is, this constant fight against gravity just isn't a permanent one. The ISS is actually slated to retire by 2030. Eventually, rather than boosting the station up, NASA plans to use a Dragon spacecraft to do the exact opposite. They'll perform de-orbit burns to intentionally lower the station's altitude. The thermosphere's drag will finally win out, pulling the station down until it safely burns up over the remotest part of the Pacific Ocean. So, what have we learned today? Maintaining a human presence just a few hundred miles above Earth requires monumental speed, spinning gyroscopes, and explosive, fiery reboosts. The ISS is without a doubt an absolute triumph of physics, falling endlessly around our planet. But it left us with a pretty massive question. If surviving in low Earth orbit demands this much constant, aggressive intervention, what is it really going to take to permanently establish ourselves further out in the deep unknown? It's definitely something to ponder the next time you look up at the night sky. Thanks for joining me on this explainer, and as always, keep learning.